Hello everyone, welcome to today's Cloud Native Data Management Day session, understanding Kubernetes design, performance and benchmarking. My name is Dean Lewis. I'm a cloud solution architect working at VMware. You can typically find me on my blog veducate.uk and also on Twitter at SaintDLE. In today's session, we've got a lot of information to get through, and I'm even going to show you a live demo as well. Realistically, I want to put a bit of a disclaimer with this session because this is based on my learnings and understanding of running Kubernetes in a virtual environment and from the research that I've done around how to design, how to look at performance and how to actually benchmark to get those metrics for performance as well. And it's still an evolving field. As Kubernetes becomes more mature, there are more tools out there, there's more information, there's more documentation, more best practices to put in place. So really this is a guide to help you start thinking about what you need to understand in your environment. The last piece as well that I'll also mention is this is going to be focused mainly around running Kubernetes in virtualization environments, because obviously I'm based at VMware and I've been a VI admin for many years, and this is how I started to learn Kubernetes, was from that background. So let's jump in. So the first thing we need to really understand is our infrastructure. We need to define it, we need to understand what platform we're going to be using. And some of these lessons in here and areas that I cover will actually cross over into running Kubernetes on bare metal as well, but we are going to be focusing particularly on virtual environments I mentioned earlier. So Kubernetes on a VMware environment or another virtualization platform, it's just virtual machines, right? But that's not just the case. There's a number of considerations from that point of view than just spin up a virtual machine. So what exactly is the platform you're running on? And how are you surfacing resources as well? Is there particular hardware characteristics, ASIC cards and so forth in your virtualization host that you want to pass through into the virtual machines of Kubernetes? We then dig into one layer deeper and think about the compute. Are we going to be using resource pools to ensure that our Kubernetes nodes our virtual machines that run our Kubernetes nodes get the right allocation of resources to them? Are you going to maybe implement something like limits? Typically these are problematic in a virtual environment because they're not very well understood. They can cause performance contention and issues artificially. So again, limits may be something that you may want to use in testing and development, but typically in production use cases you want to understand your resource allocation at a full hierarchical picture rather than just implementing limits as a one-stop fix for a particular issue. And then also anti-infinity rules. So obviously one of the great things about running a virtualization platform today is these compute plane nodes, which are just going to be virtual machines, can run on any of these nodes. But one of the things that you don't want to happen is that your compute plane nodes all run on the same virtualization host. Because if that virtualization host goes down, all of your applications are affected at that point in time. So by setting things like anti-infinity rules means you can keep that separate as well. Think about your storage, and we're going to have a slide on that as well. How is it scoped? Is it shared? So do you have other virtual machine types and workloads using that particular storage? How is it connected into the environment? And how are you going to surface it up there as well? Are you going to turn on additional protocols? So you've got iSCSI going to maybe the ESXi host, but then maybe using the NFS protocol as well to then pass directly through into the control plane nodes? Or do you want to broker it through the underlying vSphere management level of vCenter? And then finally, things like vSphere networking. Are you using quality of service today? Do you want to use quality of service going forward? Do you have an underlying software-defined networking, such as NSX, which also brings additional features and functionality that you might want to integrate? So let's think about cloud-native storage. We support that today from a vSphere and a vSAN level, and being able to expose that underlying vSphere storage, regardless whether it's VMFS volumes running on iSCSI, Fibre Channel, or whether you're using vSAN, which is a distributed storage architecture at the ESXi host level itself. Ultimately, regardless of that storage, we have a cloud-native storage control plane implemented through the CSI directive from the Kubernetes community. That gives us the ability to connect our Kubernetes platform to the control plane of the vSphere level, so vCenter, and be able to broker and expose that underlying storage, whether it's block storage or whether it's even file storage through vSAN as well, into your Kubernetes platform, so that applications such as MySQL, Redis, or others can use that underlying vSphere storage to store its persistent volumes. And the CSI driver will help communicate with the vCenter so that it can attach the storage and hard drives to the nodes as needed, and then Kubernetes understands through the CSI framework how it needs to request and detach and snapshot and so forth from that point of view. Essentially, it gives you the ability to do all of this dynamically, so your application users aren't hassling all the times for extra hard drives added to the nodes. It is the preferred method of storage provisioning in Kubernetes now. And admin intervention is not required anymore from a VI admin level. And essentially, everything's completely automated from that point of view. Digging down into it a little bit further, so let's look at networking again, touch on a little bit of storage. So here we've got our underlying Kubernetes environment. It's backed by our ESXi hosts. These communicate with over the network to one another. We've got then our physical storage, our persistent volumes, our persistent volume claims, our applications that run on top of this, and that applications inside of the Kubernetes cluster itself. Inside of that Kubernetes cluster, we're made up of multiple nodes and multiple pods that span across them, even if it makes up the same application, because there's distribution of those pods and services within Kubernetes as well, similar to distributing multiple virtual machines across a vSphere cluster. So, first thing we need to address, what network plugin are we using? So this is our CNI. Are we using something like Calico, Antrea, Flannel? There's a number of them out there. They all come with their own benefits, but also their own caveats as well. Next, we'll decide how our pods are going to communicate. So pod-to-pod communication. Are you going to layer any services in there that control that? Do you need to bring in a service which offers ingress, or is ingress going to be provided by an external infrastructure component, maybe an external load balancing service? Does it integrate with Kubernetes today? And is there anything in particular you need to do to make that integration work? Are you bringing just normal load balancing in there? And again, are these going to be external services or running within the Kubernetes cluster itself? Are the pods running local to one another? Or are they going to span across multiple nodes? And those multiple nodes are then spanned across multiple ESXi servers. If that's the case, understand the path going through this node, which is a virtual machine, through the ESXi host, across the network backbone, into the second ESXi host, then back up to the pods located here to make up the same application. What's the round trip time? Is there a latency problem? Do you need to change things like MTU to support the CNI that you've got in place? And then finally, storage access layer comes back into it. So how are we accessing that underlying vSphere storage? Or are we bringing external storage into this through maybe NFS mount points? Again, it may go over the networking stack, or it may be physical storage which is brought in through hardware cards such as HBAs if it's fiber channel storage. So again, understanding that path of traffic through your full end-to-end platform is key. Digging down a little bit more into networking. So if we think about a VMware estate, and we look at maybe just VMware's offering of its Kubernetes runtime, Tanzu Kubernetes Grid, we've got the integrated stand-up vSphere with Tanzu. So that makes it easier for your VI admins to deploy and control clusters and offer cluster services. There's a number of options there for pod-to-pod networking, node networking, so for the virtual machine out to the outside world, then has its own networking layers. Then where do you offer the different load balancing services, ingress services, and do you want to introduce anything such as pod microsegmentation? You've also got the ability as well, if you're using something like VMware Cloud Foundation, so a software-defined data center offering from VMware, then this can help stand all of this up for you, your clusters and so forth, but it then will give you an opinionated install of how you can do all the networking as well that you may or may not choose to use. And again, if you want to use multi-cloud, so you're spanning this across public cloud environments as well, then again, some of those options are going to remain the same, such as pod-to-pod networking. So these options are going to change with your particular CNI that you choose to use, some of these will have different features and capabilities. So for example, if you had MTU considerations, especially when you're creating a backbone across multiple clusters, then Antrea supports that for you, but Calico doesn't support the changing of the MTU inside the CNI, inside of your Kubernetes cluster. So when you're trying to drive performance, Antrea may be the better CNI option to choose. So again, understand the choices made around that CNI before you implement it. Okay, so next up, let's take a little bit of a step back. So I sat down for some time and I thought about those basics of, well, where does my compute come from? What do I need to know about storage and how do I integrate it? And same for networking as well. And then I thought, well, okay, but there's a lot of design decisions that we now need to uncover. So here is 4 main areas that I've focused on and thought about, and I've got some answers and just even questions to ask yourselves if you're thinking about this as well. It's not a detailed or a complete list, but hopefully you can see where I'm going. So the first one is think about your actual virtualization layer. Well, from a design point of view, the considerations and everything that you work on is the same that you've done before with virtualization platforms. It stays the same, right? So you need to think about your underlying configuration. You need to think about your storage. So if you are using that vSphere storage, or even if you are going out to external storage, what's the read and writes from the host, either over the network stack or dedicated HPAs, for example? Do you need to introduce multipathing considerations around that? Does it require additional software and plugins? Does that additional software and plugin have an effect in a Kubernetes environment? Does your storage provider have documentation about how you best consume a virtual Kubernetes environment on top of your virtualization platform when using their storage? Again, you need to think about your networking. Do you want to have dedicated networking for virtual machines? Do you want to have dedicated networking for your normal virtual machines in a shared environment, but actually a separate network stack in terms of network cards and port group configurations just for your Kubernetes virtual machines? And then finally, I think I've already brought this up, cluster usage. So is this virtualization platform going to be dedicated just to running Kubernetes workloads? Or is this going to be shared across other applications deployed in your environment, maybe your back office systems, for example? For your Kubernetes cluster itself, so standing up the virtual machine, think about that. Think about the virtual machine resources. Are you going to create big virtual machines with lots of CPU and memory added to them? But again, you're going to hit pod limits in there at some point. So will you actually fully utilize all of those resources? Or is it better to deploy a smaller number in resource sizes of worker nodes, so you have more worker nodes deployed, so you can span all of your pods and services across them? Think about NUMA configuration. So that can be quite a detailed discussion design with your architects and your virtualization team. That's how you design your virtual machines to fit in the memory space mapping and how that memory space mapping communicates across the motherboard channels to the CPU for best performance. If you've got a highly transactional application, this is some of the areas where you'll get key gains with the right design and the right deployment. And then we come back to those anti-infinity rules, keeping your worker nodes away from each other where possible, so that if one node dies, as in a virtualization node, and it takes the virtual machines with it, your other virtual machines and worker nodes are still running, and they can take over the pods when the controllers inside of Kubernetes notice that those pods are no longer running. Then we get to the application layer. How are you actually going to deploy your application? You're going to have self-service access? Are you going to give developers full access to the cluster? Are you going to have CI/CD pipelines that do this for you? You're going to let the Kubernetes cluster decide how to manage resources for you. So you give it a pod and say, run this bit of code for me and container, and off you go, and then hope everything gets scheduled and worked out in the background. Or are you going to start to set resource limits on pods, containers, and namespaces and quota management? And again, does this link back into your application deployment methodology? Will you use selectors for placement logics of pods and containers as well? And does this selector and placement logic revert back to anti-infinity rules and how you've designed maybe availability of the Kubernetes cluster on top of your virtualization platform? And then future planning. It's always a little bit harder with future planning, but how are you going to scale? Is this going to be a manual approach, or is this going to be automatic? How do you scale pods? How do you scale up, so increase your VM resources, and what's the effects of doing that? And scale out, So how do you increase the number of nodes? And that goes back to the Kubernetes cluster design here on the left-hand side. So these are a number of the questions that maybe I don't have all the answers for you today, but you certainly need to think about when you're starting to architect and deploy a Kubernetes environment on a virtual environment. So this leads me quite nicely to the next piece. Some of these decisions are going to be thought out and proven through testing of your environment and understanding the right data. So monitoring is a key point to that. There's two areas of monitoring to look at. The first one is infrastructure up. So we look from the virtualization platform up into your Kubernetes cluster. And that's very important because especially when you start to go live with services, if you have a phone call come through to your service desk from your application owner and they say, hey, this pod is running really terribly and we think it's a virtualization estate that's causing the problem. How do you know where that pod's located? Because that pod lives inside a virtual machine, and that virtual machine lives inside of a cluster of hosts, and that could run anywhere. How do you troubleshoot that? Well, vRealize Operations from VMware. It gives you the ability to monitor all of your vSphere estate, and it goes even further through management packs so that you can connect to your Kubernetes cluster, discover how the Kubernetes cluster is built, which ones are master nodes, which ones are worker nodes, and then what pods and services are being deployed in there. However, it doesn't give you metrics from inside your actual containers themselves, so the application. So there is a limit there. You've got that additional visibility. How do you go one step further? You could use Prometheus as an open source alternative. Prometheus does a great job out there. It's used by a lot of Kubernetes community today. It's very extensible, and you can also get metrics on that from both your virtualization estate and your container environment. But Prometheus isn't going to pull them together. So in Prometheus, you might have a problem with, hey, I can see this virtualization host running okay at the moment, and I can maybe see which virtual machines are there, but I can't really see into the Kubernetes environment and link all of these things together in a topology type view like vRealize Operations can. Also with Prometheus, do you install that inside of your Kubernetes cluster, or do you have an external deployment? How do you manage that? And even kind of think about that for HA and availability as well. And then we get back to the end user, the consumer of the platform. What's useful to them? So then this is the application down approach. So we've got Tanzu Observability, again from VMware. Gives you full application level visibility and granular detail into what's going on in your application. Links that back to business SLAs as well. So you may have 100 pods running and want to make sure that your website is 99.9% uptime or availability connecting to, and it runs the correct microservices at the back end to show the right content and information to your end users. Tanzu can view all of that, and you can help write business rules. Say, well, if this number of pod goes offline, then my availability is affected, and it's flags alerts as well. You can also use that data as well to understand how your platform in an application is running, and do you actually use that then data to scale your platform as necessary? So let's talk about scale and resource management. Again, thinking about a VMware deployment in particular, but you could abstract these concepts away to other platforms as well. Where does the scale and resource management come from? So I'm going to start from the infrastructure up view into my Kubernetes cluster. So we'll start off with the ESXi host. We can just scale that with new hosts in the cluster, and then we can deploy more virtual machines with more physical resources. The problem with this is it takes time to do that. If we run out of physical resources in our environment, we need to create change requests, we need to get sign off from our finance department, and then we need to go and rack, stack, cable, and connect all of those hardware pieces as well. That takes time to do that. Everything else off this layer, as long as the physical resources are available, can be pretty instant. So if we're using a vSphere with Tanzu deployment, which is native integration of Kubernetes into your virtualization platform, we have this concept of vSphere namespaces, which map back to Kubernetes namespaces and how that architecture deployment works. We can scale the resource management there if there's limits in place. We can then do that at a Kubernetes level from an access point of view. We can also scale the deployments inside of these namespaces. If we're looking at the virtual machines, we can scale out with additional control plane and worker node counts if we need to. We can also increase the memory usage of these. So we could create a new virtual machine that is linked to a machine type, machine set inside of Kubernetes, give it the profile of what the virtual machine sizes should be within the vSphere environment, and then scale that up and scale down our older machine set to delete the virtual machines. It's going to be a crossover where you're using more resources than you actually need for your cluster at that point in time, though. And again, some of these things can be managed through, if it's Tanzu, the Tanzu CLI. Some of these things could be managed through the vSphere interfaces, the vSphere admin. Some of these things can be managed by kubectl. And again, that could be used by your application developers if they so need. And then we go further down the line. So scaling continued. So think about our application, our deployment. So we need more resources, but how? So for our services and pods we've deployed, we could just use something as simple as the horizontal pod autoscaler. It scales the number of pods in our deployment replica set, stateful set, based on observed CPU utilization, for example, of the application. Or you can add custom metric support in there as well, or other application provided metrics as well. So you may set a rule that says, we always run 5 pods as part of this deployment, but when we hit 50% CPU usage, we want to increase by 2 pods at a time. If we need to go a little bit bigger and we think about a cluster overall, we also have a cluster autoscaler that we could configure. It's a tool that automatically adjusts the size of your Kubernetes cluster when one of the following conditions is true. There's pods that have failed to run on the cluster due to insufficient resources, or there's nodes in the cluster that are underutilized for an extended period of time, and the pods could run on another node if they scaled down the size of the cluster. And that's great, because that scales up and scales down the size of your cluster as you need. However, that's configured at cluster deployment. So if you've already got an existing clustering environment, that may not be possible to do. But maybe you could replicate that functionality in CI/CD pipelines, triggered on certain information from your monitoring tools, potentially. And again, you could always go back to the good old method, which is manual scaling of pods and clusters when someone comes knocking on your door and complaining that things aren't working right. Okay, so let's think about benchmarking tools. So let's think about how we start testing our environment, getting some of these metric data, understanding the baseline of our environment. Again, this isn't a definitive list. This is just me looking at a number of open source projects that are out there today, and one paid for project on here in particular. And I've kind of broke it down to a couple of different areas, thinking again about how I test my platform, how I test the storage, the networking, and then focus on the application. And another important part, which is security. So from a custom management and lifecycle point of view, we can use something like KBench. It's a framework to benchmark the control and data plane aspects of Kubernetes and stress test based on your configuration. And I'm going to show you that in the demo as well. With storage, we can use something like Kubester. It's a collection of tools to discover, validate, and evaluate Kubernetes storage options inside of the Kubernetes configuration itself. It also helps from a data protection point of view. Does your CSI support snapshot control, for example? Is it configured correctly? Then you can run FIO tests to stress test the performance of your storage system. Again, there's options to do that just with KBench, and it actually uses FIO too. For networking, again, the same name comes up, so KBench. Networking is one of the areas where I really struggle to actually find some tooling to help us with this. But we really need to do that pod-to-pod communication test. Maybe we are actually communicating across separate clusters and we have some sort of service mesh technology that's been implemented. How do we test those types of communications? How do we test if we've made MTU configurations and we're going across nodes to talk between pods? Then we get to the important part, application build and load testing. So Weathervane from VMware is an application level performance benchmark. It deploys and stress tests at an application level, and you can do that until the point when your cluster breaks. And maybe that's a good thing to do, is understand at what point does your cluster fall over. The Kubernetes API stop responding, storage becomes unusable, the networking saturated. There's other tools out there such as K8 Test Suite, which also focuses on load testing your applications. We've got KubeMonkey, built on the idea of Chaos Monkey idea from Netflix. So going around destroying things in your Kubernetes environment. And how does your application respond to that? Does that cause problems? Does your monitoring system pick this up? Do you need to have some automated actions to deal with when pods just randomly disappear in your environment? Powerful Seal is another project which takes this idea even further and starts to affect your cluster nodes as well. So what happens if you have an underlying problem with your virtual machines? And then a really key area, so although it may not kind of directly affect performance, it definitely does in terms of configurations, is security compliance. So we have Runecast, that is the one paid for tool on this list so far. Kubernetes Analyzer focused on CIS benchmarks. We've got KBench from Aqua Security, which looks at CIS benchmarks. And we've also got Project Sonoboy as well, which does a number of performance tests and CIS as well. So security is really important, but also when we start to implement these security compliance settings, they can have a negative effect on our performance, and we need to understand that. And really, with these benchmarking tools, what you need to be doing is running these as soon as you create your Kubernetes clusters, or you trial and test configurations, understand your baseline, and then keep running them again and again and again. When you're in production, it might not be always the best to run some of these tools again in production because you don't want to negatively affect the cluster in terms of performance, but you do need to find a way as well to find out if you start to deviate from the baseline as well. So I think that's enough slides. We're actually going to go into a live demo now in my environment, and we're going to look at two of the tools off that list. We're going to look at Kubester from a storage point of view. We're going to look at KBench, which does a suite of these areas as well, and some of the outputs of KBench as well. So this is my test lab environment. I'm just going to do a quick K get node. So whenever you see me type K on the screen, that's actually just an alias for kubectl from that point of view. So the first thing I'm going to do is I'm going to move into my Kubester folder. Inside of my Kubester folder, I've got my Kubester software already there. I've not moved it into my local user bin folder. And then I've got some FIO tests as well. Now you can get these as examples from the Kubester GitHub repo, but because it's using the FIO performance tests, and I've been out for many years for as a piece of software for doing this with it, it's still one of the best and most used out there for such a simple product. There's many examples out there that you could use as well. So the first thing I'm going to do is I'm just going to run Kubester in my environment, and if I just put / on there, it's just going to check. So it checks my validated version. Have I got RBAC enabled? We can see here there's a warning about using the beta for the CSI driver. You can see that we can't support snapshots in here, so that might be a problem from a data protection point of view. You can see the storage class that's available, and I can see how I can perform a FIO test as well. So the next thing that I'm going to do here is I'm going to do a cat on the FIO test. Let's do sequential write from this one. And we can see here we've got a number of how many what we're going to do is we're going to do a write test, how many jobs are we running, what the size of the files we're going to create inside of the persistent volume, and what's the IO depth length in terms of stress testing. And then the next thing that I want to do from here is I actually want to now run this. So I'm going to run Kubester -s to specify my storage class that I want to create the PV against. Going to run that, tell it we're running the FIO test, and then which file to use for those settings, and then how big do I want the persistent volume to be. And the persistent volume is obviously going to need to be bigger than the size of the file I'm writing inside, otherwise you could cause problems there. So we're going to go ahead and we're going to create that. We can see it creates a persistent volume claim straight away. And if I bring in my other terminal window, so unfortunately my Linux isn't that great where I could use tmux to multiply that, but if I do k get pods, oh, that would help if I could spell the word pods. Just do it in the default namespace. We can now see that we're running this Kubester FIO pod, which actually links here and tells us what we're going to do. And it's going to run that test inside of that pod going forward. And if I do k get PV as well, I'll just bring that across a little bit more. You're going to see you've got that claim, we've got the PV that's been created as well in the environment. And that takes roughly, in this environment when I run it, about 60 seconds or so. So we're just going to speed things up for that to finish. Okay, so we've finished now. We can see all the details, can see all of the outputs. Just take about 61 seconds there, as I mentioned. Again, we can see the job settings, we can see what happened, so at an IOPS level, what the bandwidth was, we can see the max, the minimum, the averages as well, and particularly, quite happy with that in my environment. But again, if we were doing maybe some tweaking of settings, then we'd run this again and again and again, see what the effects of these tweak settings are. So that's kind of Kubester in a nutshell. So that's the first test we're going to look at. The next one is we're going to look at KBench. So I'm going to move into my KBench folder, and then I'm just going to quickly clear my screen to clear things up here. So KBench has a number of pieces to it. So if I do an ls here, inside of KBench, we've got an installation script. It will actually do a KBench CLI tool. So if I do help on here, we can see that I've got it installed, we can see the number of options, and we can actually run KBench directly ourselves, or we can actually do the run sh script. The run sh script does a few more things. It's actually going to put things into a nice folder for us and copy across the various log files and everything that we're interested in. So what I'm quickly going to do is I'm going to show you how to run KBench raw at the moment. I'm going to show you how to use the run script, which kind of makes things a little bit nicer for us today. Before I do that though, I just want to talk a little bit about configuring the KBench tests themselves. So they live under the folder of config. There's a number of well-documented examples here by KBench. If you run just KBench as a tool on its own, it's going to run this default folder for you. Or you can specify another one of these folders instead. Inside of these folders, we've got some configuration files. This tells us how we want to create namespaces, the application that we want to apply in there, the containers and so forth, how long it runs for. And again, you can clone, copy, tweak, change these as you need to. So let's think about how we run this as well. So using this run sh script, so I'm going to do /run.sh, I'm going to paste the rest of my command in there. So we're going to tell it that the run is called the Cloud Native Data Management test. I want to run this particular set of files, so it's going to look for this folder inside of the config folder that we're running from, and then the output is going to be sent into the root of the folder that we're in, and it's going to create another folder like this as well to save all of the results, outputs and configurations in, so that we can dive into that in the future and basically have a full set copy of everything. So let's run that. So we can see here as it's running that there's a KBench log we can check for details, and if we look at my screen above, there's a KBench log file that runs at all times as well. So if I bring across my second screen again and I go into the cd KBench folder, one of the things we can do is we can tail that log as well. So we can see what's happened at the moment. So we can see that one of the benchmark runs is actually completed. So at the moment, that's actually running from the last time that I ran this as a test. But we can see some of the details that's in here as well. We will now have, if I do an ls here, that structure for the CNDM test. And if I go and cd to this folder, and I ls from that point of view as well, we can see that it's copied in here this particular test that we're in, that we started to run. So I'm going to do cd in there too, and I go on ls, and we've also got a KBench log that runs in there as well, and a config JSON file. That config JSON file is basically the configuration that we're interested in terms of this configuration here. So again, it could have been tweaked, it may have been changed by people. So again, when you've got a copies of each of these each time you run, you also know the exact configuration that these will run against as well. Again, I can tail this KBench log, and we can see some new updated information in there as well, because the KBench log's been redirected to this folder. But if I just ran the KBench tool, it's going to use the defaults and it's going to use this KBench log in the main part of the folder. We can see here it's created some namespaces and so forth. So if I now do kgetns, we can see some namespaces. Now these namespaces admittedly were created earlier because I actually had run this obviously to make sure that it works the way that I expect in my environment. So this will update, but then it will still create new pods and new services. Once you finish with all this, you can actually run the cleanup.sh and it cleans up all these types of things for you as well. But it leaves them in place so that you can go through and manually check the configuration inside of your cluster as well. Now, takes a couple of minutes for this KBench to run in the environment. So I'm just going to wait and we'll speed the video up to completion. Okay, so it's finished now. We can see it's where it's wrote the logs to. We can see that it's exited, the benchmark's finished, and we can go in and we can actually explore that further. Now, just to save time, I'm going to do a here's one I made earlier moment. So I'm going to use my Windows machines because it's easy to browse through, and especially for the video recording. But I've got a folder here where I run a more in-depth test. And you can see there's a number of things that have been run here. So, for example, in the Redis one, we've got the KBench log itself, that particular test. We've got the configurations. We've got the logs from the environment as well if they were outputted. They weren't in this particular one because I had a slight problem running the test for the Redis stuff. We've got the configuration JSON for this, obviously, test itself. We've got the aggregation of any results that are brought through. If I then go back up, so if I go into something like the network internode one, which is a little bit more interesting, we've got, again, all these YAML files. We can see how the iPerf service was created and set up. We've got how the pods were created, so the client server point of view. And so I can actually run some of these things manually if I wanted. Again, I've got the individual KBench log, and then if I go into this folder here, you can see the pods that I've run, and then we can see the outputs of these pods as well. So I can see the server setup and output, so I can see if there's any errors, I can see the server was up and running and what happened there and how much information was sent back and forth. And then I can go to the other pod, and pod 2 is the client. I can see all of the client side of things as well from a testing point of view. So there's quite a lot of information in there to dive into. And again, you may need some other tooling to help interpret that or plot these on a charts and so forth. But the main thing is that the data is there. Again, play around with this in your environments. You may find you break some of your environments if they're on the smaller side when you do things like this. I actually ran this test, but I had a couple of issues pulling down some of the Redis pods because I was getting... I think it was, if I remember correctly, Docker rate limit, for example. So again, a few things there that I had to overcome. But again, mainly the point here is to show you the tooling that is available and how you can get used to some of this stuff. Okay, so that's the end of the live demo for today. I'm going to go back into my slides and I'm going to summarize and finish off this session. So thank you very much for your time today. Really appreciate it. Please do reach out to me directly through my blog post, theeducate.co.uk, or on Twitter, @SaintDLA. Really like to know if you're using any other tools in your environment, what you found, if you've put any standard best practices inside of your environment as well. This is an evolving space, so I expect in the next 6 months we'll see even more information out, and maybe I'll be back again with an updated version of this presentation. But from me, thank you very much. Enjoy the Cloud Native Data Management Day sessions and enjoy KubeCon USA 2021.